Hello, and welcome to the OASIS Understanding Big Data Using System Dynamics and XMILE webinar. My name is Dee Shore. I will be your moderator today. We have three speakers. The first is Steve Adler from IBM. The second is Karim Chichakly from ISEE Systems. And the second is Bob Oberlein. We will begin with Steve.
Oh, am I the presenter now?
You are.
Good morning, everyone. I am Steve Adler from IBM, and this morning we are going to talk a little bit about big data, system dynamics, and XMILE. You're all here because we have just created a technical committee in OASIS to review the specification called XMILE with a broad international audience. And we hope that the presentation we've created this morning to introduce you to these ideas will challenge and captivate you, and that you will join us in our journey to create an international standard for system dynamics. I'm going to take a little unconventional approach to this presentation this morning. Rather than provide the normal introduction and charts, I'm going to show you a demo of big data simulation. And then we're going to discuss how this simulation plugs into system dynamics and show you a real system dynamics model, and then talk about XMILE. We're doing this because we realize that big data means a lot of things to a lot of people, and sometimes it's hard to visualize what it looks like when you do it. So what I have on the screen right now is a simulation that was created by IBM using one of our products called Streams. Streams is a product that analyzes streaming data. It's not data coming from a data warehouse or from any other repository. It's data that comes in over the pipe at high velocity. And in this case, what you're seeing is a map of New York City. And on the map are blue dots, and those are cars. Now let's see if this works. Can everybody see my screen? I hope you can. I'm going to run this little demo. And what this demo is showing are the cars traveling across the city in different flows. Just normal people driving about, doing their business, traveling through New York City in thick, congested streets. And in the moment, we're going to simulate an event. And this event, in this case, is going to be the outbreak of infectious disease. And as you can see, we're going to plot the outbreak, its specific parameters, and so we're simulating what will happen to these cars as they pass through an area of infection. And you'll see in a minute that the cars that are infected by the disease turn red. Now, of course, this is a simulation, but if this was real time, we were monitoring cars, we could not only monitor the infectious area, but based upon their past behavior, we can forecast where they're likely to go. And that's the purpose of the streaming environment, is to analyze data coming in real time, very, very fast. In this case, it's GPS positional data of cars going through a city, simulate an event, and then use the past behavior of the cars to analyze where they're likely to go and who they're likely to infect in the city. This demo continues, and you can see now that we're down at a lower level looking at the cars. And you could imagine if this was an infectious disease, that these cars are carrying the infection throughout the city, and as they potentially get out of their car and meet other people, the infection could spread. You could look at this and say this is a very typical type of agent-based modeling environment in which you simulate impact on independent actors or agents. However, in this case, we're trying to simulate that we could be reading this information in real time and reading the real-time data of cars and then running a simulation. Now, that shows you where they're likely to go. It doesn't tell you what the people in the cars are likely feeling, what they're likely to do, or what the rates of infection will be over a longer period of time. For those types of simulations, you need a different type of modeling environment. And that's something we want to talk a little bit about today. That is, system dynamics is a discipline for understanding long-term tertiary consequences from different types of events. And it's particularly useful at analyzing complex data in large environments and ecosystems. We all know that our world is becoming so complex, it's becoming very difficult to understand all the different interconnected and interdependent pieces. So we're beginning to understand that cause and effect, one cause, one effect, doesn't quite answer all the complexities of our world. That the ecosystems we live in demonstrate that just changes in one area don't just affect another nearby. If you change the course of a river, it doesn't just affect the animals living in the river, it affects the broad ecosystem far beyond the river for hundreds of miles. It's an idea that really is only 30 or 40 years old, and that we're all becoming increasingly aware of as we experience global warming and the impacts on our environment and the non-predictable impacts around the world. And we believe very strongly that we need new tools to understand the ecosystems, not only of the natural environment, but also of our own creation. This was a project that IBM ran for the city of Portland a few years ago, in which we designed a system dynamics simulation to help the city understand the impact of public policy in one domain and how it might affect many others that don't seem that obvious. We built a large simulation for the city, part of our Smarter Cities initiative, to simulate how policies will affect human behavior and give the city a safe test environment to predict those impacts, both the obvious ones and the non-obvious ones. The chart you see in front of you actually shows how changes in urban density or what are called small neighborhoods and smart trips impact not only the convenience of shopping and populations, but also carbon emissions, obesity, a whole variety of different factors that are really difficult to see unless you have a model that illustrates those impacts and shows the consequences across many different domains. One of the things that we've learned through system dynamics is that a structure of a system itself produces its own behavior, and people often don't know what they don't know. And so it's our task to understand systems and behaviors, that is, the indirect consequences of our decisions and the tertiary consequences of our policies. And it turns out that's not a really easy thing to do. It's not an easy way of seeing the world. But we can, through system dynamics, model these complex ecosystems and simulate policy and validate outcomes over time. A systems dynamics model is not like a process flow or an agent-based model that shows that predicts behavior for short periods of time. A system dynamics model is an explicit modeling language that depicts changes over long periods of time across many different areas. And so what we want to do now is take you through from that car model that we showed earlier and now describe how we could take the data that we gathered from that map environment, that geospatial data, the blue cars and the red cars, and now show you what it looks like in a system dynamics model. And just imagine for a moment that the data we took from that model is now populated into the chart in front of you. And Karim will now take us through this example. Karim?
Thanks, Steve. So looking at this model, very briefly, I broke up the city into two different regions. In region 1, we're going to have the infection event, and region 2 we won't. You could have as many regions as you wanted to. Into each of these regions, you have cars entering and leaving the regions, and you also have cars moving between the two regions. You also need to track, once the event happens, who's infected or who isn't infected. So we have different infections in different regions, and ideally, you can apply a policy that will contain the infection in region 1 so it won't spread outside that part of the city. Down here at the bottom, so the infections, who gets infected is changed by the infection rate, and of course, someone in the city, when they leave it, if they leave region 1 and they're infected, then there's no longer somebody there. So people can leave they're still infected, but they can leave, and we have an infection event that comes in region 1 and has that happen, and then we also have the transfer of infected people from region 2 to region 1 and from region 1 to region 2. So that's great. That looks at a high level and what's happening, but we can also start to add policy options here. So if we look at the original infection part where we have people becoming infected, we have an infection rate and we have this infection event happening, but we also have people that are entering the infected area, people even within region 1 who are entering the infected area because it happened in a small area. So those people that enter become susceptible to infection and they can become infected at a certain rate. This would also be people outside if they had outside the area. So in each region we have people, we have areas that are infected, areas that are not infected, and possible infection rates. So how do we control that? How do we intervene? What policies can we adopt to try to reduce or curtail the spread of the infection? One of the things we can do is we can start broadcasting information to the public on radio, TV, on the internet, to try to make them aware that this is an area to try to stay out of. So this may be, so we broadcast that and we tell them, you know, please stay out of this area. Unfortunately, that might also make people leave the area. And that broadcast effect is multiplied by some word of mouth, people talking to other people. And the broadcast effect also, there's a certain time they start doing this, and that's a response time. So the response time is one of our policy levers we'll see in a minute. And the awareness of this infection is hopefully going to slow down those people entering that area. We can also quarantine the area by sending police or responders out there to try to block entrances and exits so people don't spread beyond the limit. And how well we do that is going to be based on the size of our police force and how fast we can deploy those police. And we are going to start doing that at some certain time that is going to be based on our response time. So we have two policy levers in here. The deployment rate could be another policy lever, but two that I'm looking at, which are the time that we respond to start broadcasting this and how long it takes before we start. The police are able to respond as well. If we look at those different options and we look at the different settings for those options, then we can, and we simulate that on our computer, then we can see several possibilities. Curve 1 here, you'll notice they all pretty much start the same way. This is the infection. This is how many people are infected. Curve 1 is if they don't respond at all, and curve 2 would be a sluggish response. It's still really taking a long time, so more people get infected. Curve 3 is what would be a reasonable response, and curve 4 would be a very quick response. What I'm not showing here is how fast it would spread into the other areas, and in all of these scenarios, the way it's set up in this model anyway, there'd be damage control outside region 1 as well. So system dynamics, we looked at the agent-based model, and the agent-based model allowed us to look at what was happening in the near term based on what we saw people doing in the immediate past. But system dynamics allows us to look at things from a broader perspective. It allows us to look at the longer term. It allows us to bring in other parameters that are harder to track on the agent-based model. In particular, it allows us to easily experiment in a policy space and see what happens, and it allows us to look at what's happening with the tertiary services over time. So I looked at the police force and how we might broadcast, but we also have EMS services coming on, and they've got to come to the area and help, and they have to get people out of there to the hospital. We have effects on the hospitals. We have effects on how long it takes to treat these people. So there are a lot of tertiary effects that we can model as well and see what happens over time. We can feed these with live data. We're here to talk about the XMILE standard, and the whole point of that is to enable these simulations across a broader range of applications. Currently in system dynamics, we operate in an area where there are no standards. There's a base level standard of the language, but beyond that, everyone has their own extensions. There's no standard file format to exchange files. The systems that exist are all closed, and there's little cross-fertilization with other systems. There's little integration with other systems, for example, IT systems, big data systems. There are people that do some work like this, but it's very limited. There's no portability of models. There's little sharing except through publications, because unless you have the same software, you can't run the same models. And there are important developments that are made in this field that aren't archived well. So XMILE addresses all of these issues, but also opens new markets because it makes it easier to enter in big data, to throw simulations in that are fed by real data from big data, or to take pieces of big data and try to tie them together in different ways. It opens new markets in social media as well, in analytics, and allows people to develop. It opens things up, so you can develop things in more areas, basically. It also allows reuse across the different system dynamics platforms, and also sharing of substructures, which can become very powerful. The technical committee itself is having our first informational meeting on July 23rd at 3 p.m. and the technical committee meeting, the first one, will be on the next day at 10:30 a.m., both at the International System Dynamics Conference in Cambridge. I have a link here if you want to join OASIS. If you want to join the committee, if you're already a member of OASIS and you want to join the committee, this second link is how you join the committee, and the specifications are available right now on the IC Systems website, the current specifications at this address. And I think that's to you, Bob.
Bob, you need to unmute yourself. We see your screen.
Sorry, I clicked and I missed. I apologize. I'm Bob Eberlein. I'm the Vice President of Electronic Presence of the System Dynamics Society. And I wanted to say a few words about System Dynamics, its history, and make a plug for the upcoming conference, which is where the first meeting of the Technical Committee for XMILE will be held. So System Dynamics is a field that has a pretty long history, and interestingly enough, the early work done in the field was done using a language called Dynamo, and it was one of the few sets of sort of scientific work in, well, social science work that was really replicatable, and it was replicatable precisely because the Dynamo equations, which were pure text, allowed other people to take those and use them and get the same results as they would have seen elsewhere. So there is actually a bit of a history of being able to replicate things with with the language in System Dynamics, and what's happened, which Karim alluded to, is there's been a divergence as more vendors come in place and each develop their own standards, so there's no longer a common language that's used within the field, and as a consequence, we no longer have the ability to hold things together. So XMILE is very exciting from the perspective of System Dynamics Society because it will once again bring us a level of standardization that will allow us to archive things that have replicatability across vendors in a significant way. So the System Dynamics Society, if you want to find out more about that, there's a link up here, systemdynamics.org. And the other thing, of course, is we have an annual conference, and this year it's July 21 to 25. It's being held in Cambridge, Massachusetts. We have almost 300 papers that are being presented, many of which are applications to a variety of different areas in public policy, energy, the environment, healthcare. So there's a lot of work that's being done, and a lot of that work is being presented at the conference. We hope that some of you might be able to attend that. The opening meeting for the technical committee will also be held at the conference, and there will also be an informational meeting that's open to anyone in the community, not just members of the technical committee. Just a final note, today is the final day for early registration, so prices go up after today. So if you're interested in the conference, it's very timely to check it out, conference.systemdynamics.org. So thank you very much. I'll turn it over to you, Dee.
Very good. Thank you, Steve, Karim, and Bob. We've got some questions now, and I want you guys to feel free to sort of jump in. We're going to keep this informal. I'm going to read through the questions, and again to the audience, feel free to go ahead and type in your questions in the question box, and we'll get to as many of them as we can cover. Again, it was a short presentation, so we've got some time. The first question is, are you tracking individual cars, people, as in an agent-based simulation, or just using aggregate streaming data to calibrate global variables in an SD model in which individuals are treated as homogeneous in the aggregate?
Yes, so I'll take that. Yes, we are using aggregate streaming data and looking at things in the aggregate. So the individuals are treated as homogeneous, and that's the nature of SD, right? That's the difference between that and agent-based.
Steve, Bob, do you have anything to add? No? Okay.
Just a short note. A short note that the current development of the XMILE standard will be for classic system dynamics work, and extensions into things like the ability to accommodate discrete event and agent-based simulations is something that will be considered for the next version of it.
Okay, great. Thank you, Steve. Here's the second question. Reuse of models means that models conform to certain quality standards. How will this be addressed?
Dee, did you get the note from...
I'm sorry, would you like for me to repeat it?
A quick note on that. One of the biggest things here, I understood that. So one of the biggest things here is actually replicatability. So getting to a quality standard requires that you do things right, but it also requires that other people be able to do the same things to make sure you haven't simply done something that can't be done by anyone else. And what XMILE really is addressing is the ability to replicate work that is done by other people in different formats. It doesn't in and of itself guarantee any quality, but unless you have that ability to replicate, quality is very hard to improve.
Yeah, I think that was great, Bob. Thank you. I don't know, Dee, if you got the message from Steve that he's muted and can't unmute. I think he wants to say something.
Okay, hang on. How's that? There you go.
Now I'm good.
There you go.
Yeah, no, Bob gave a great answer. I can't add to that, but thank you for unmuting me.
Sorry about that.
No worries.
Okay, let's go to the third question. This one, you guys may or may not be familiar with. I am. It's the emergency work within OASIS. But let me give it a pass, and you guys tell me what you think. Hold on a second. I'm somewhat familiar with XML Messaging Standards, which our organization sponsored the development through OASIS and facilitated development by users. Okay, there were the EDXL standards. How is this project approaching development via messaging standards or model exchange? That may or may not be something you guys can answer.
No, I can't answer that.
Okay. Chip, I'm familiar with your question. I'll send you the answer offline. Did you want to take a pass, Karim?
Yeah, I am familiar with that standard, and that's it's really not related. It's really trying to improve communication between different areas, and this is really trying to look at the effects of for example, in emergency management, the effects of the deployment and different deployment strategies over time rather than trying to communicate.
Yeah, but maybe I'll pick up on this. Actually, something Bob said reminded me of something. You know, we have to take responsibility for showing a link between the streaming environment, which may look like an agent-based model, but it's not. Even though it's a simulation of a streaming environment, if we were using a streaming environment to capture the data, it would be coming in real time, and we would be using computers to calculate the past behavior of the cars and forecast future behavior. Last year, I lived through Hurricane Sandy here on Long Island in New York, and had the frustrating experience of going for 3 weeks without electricity. And my neighborhood wasn't particularly hard hit by the storm, but we were hard hit by trees that knocked out transformers. After the storm, the first question that came to my mind, or even during, was where were all the simulations, the weather pattern simulations and first responder simulations for predicting the impact of the storm? We had had Hurricane Irene the year before, and I wondered, didn't anybody have a simulation that could have predicted the impact on power lines and gas supplies and other things? And it turns out there were. There were lots of simulations. There were weather pattern simulations. There were first responder simulations. Many organizations had even predicted that storms like this would happen and that millions of people would be without power for weeks. The problem was that none of the simulations were connected. They weren't connected by the groups that did them. They weren't connected by the methodologies that were used to create them. They weren't connected by the outputs of each simulation to each other. So we had agent-based, discrete event, maybe even system dynamics, weather pattern, all different types of simulations that predicted different aspects of an event like a massive storm hitting the New York area, but nobody thought about connecting the dots. And that's an important thing, and that's why we presented the big data and system dynamics scenario today. Because we really think it's important to start connecting the dots. It isn't necessary, as Bob said, to have a global standard that unites every simulation modeling environment to still be able to pass data from one simulation to another, to evaluate, so that each one can do what they do best, to predict the pattern of cars passing through an area, and then to simulate the impact of public policy on an infectious disease rates as it goes through a city over time. And that's what we're trying to accomplish with the standardization of XMILE, is to provide organizations around the world with the ability of connecting system dynamic simulations to other types of modeling environments and simulations, so that in the future, when we have large events like Hurricane Sandy, policymakers can connect the dots between different simulations, and make accurate forecasts of how these events will affect all of our lives. And that's what we feel is really important.
Great answer. We've got lots of really good questions here. Here's the next one. Is there any beta version of XMILE, and how is it going to operate?
Karim?
So there's a proposed version of the standard that's on the IC website that I gave you the link to earlier. And those are the starting documents for the committee, and we'll see where it goes from there. What's in those documents has been implemented in IC Systems products, so people can play with it and see how it works. And we're anticipating it to be implemented in other products as well, so that we can look at the interchange as well. But the key thing is we have a base implementation already that we can play with, and we have a draft specification that people can look at and comment on.
Steve, do you want to add anything?
Next question. Nope, I think that was great.
Okay. We're getting a lot of echo on my voice. I'm sorry about that. If you guys could just mute real quick while I read this question, that would be great. How do we distinguish between initialization data that may come from the DE modeling and subsequent patterns? For example, do we also have the potential to import past patterns of behavior? Do we have an answer for that?
That's another one for you.
Do we have an answer for that?
Well, traditionally we do this using past patterns of data, so that we import that. The difference that we're talking about here is we're talking about being able to take live data and pulling it into the model and using that to make decisions in real time about what's going on, or at least to look at the impacts of our decisions in real time against future outcomes. So bringing in past data is in system dynamics anyway. That's something that we do all the time right now, and it's not really part of the style. It's the standard. It's really more part of the methodology and the way that we practice it. But we're trying to reach out and broaden this to look at data streams coming in and how we can use those to get the model to give us information about the decisions that we're making in real time and what impacts those are going to have over the long term, so that we perhaps can avoid unintended consequences. That's our hope.
Okay, great. Let's just keep moving through those. We still have some time. Can you show us a sample of what the XMILE standard says about how some part of the SD software should deal with? It says something, but I'm assuming it just means, you know, an issue.
Okay, so hang on one second. I'm going to bring up an example.
Okay. And Steve, I just unmuted you.
Yeah, maybe while Karim is doing that, I'll just make a comment about the question before about the data values. Normally in a system dynamics model, the information in the stocks are inferred values. That is, the modeler comes up with data. They make inferences about the values of stocks and how they accrete or decrete in the flows. But there isn't anything in the example we just showed you from the streaming data. We're sort of asserting that we could be capturing that streaming data live and not only plotting the course of the cars, but during the event, but also after. And so there's totally open for discussion in the course of the technical committee about how to enhance XMILE, if required, to include the ability to link to live data. so that values in stocks don't necessarily have to be inferred, but rather could be derived from either streaming applications or repositories, and so that the models, the simulations that would be run could be run on live data.
Great, thank you, Steve. And that's important. There are already some things defined in the standard for connecting to external data. There are already some things that are there. I'm not quite sure what the specific aspects someone was asking about relative to XMILE, but to XMILE. But here is a very simple model, and this would be the representation at the simulation level. There's also information about the display of where these things are, that their positions, their sizes, that I'm not showing here. I'm just showing the basic equations. So in this model, which is just this section here, we have, stocks with their values, the list of the inflows and outflows, and then for each of the flows, we have their equations. We have converters here that in their equations as well, including a graphical function down here. I hope that answers part of the question.
Okay, this is great, guys. We got lots of questions. Okay, here's the next one. Basing the behavior on the past data doesn't account for a change of behavior due to an event. Is that correct?
I think Bob can also address this, but I'm going to just jump in here for a second. In system dynamics models, one of the fundamental beliefs is that, the structure determines behavior, and that's one of the things that Steve talked about earlier. So if the structure determines the behavior, the past data, we're going to feed in the past data to try to reproduce historical behavior to try to give us a sense that the model's valid and that we have confidence in the model. But we can then apply the event to that structural system and see how it impacts the results. Yeah, the past behavior isn't going to tell us what's going to happen when the event occurs, but the past behavior can help us, and our theories about it can help us develop the structure of the system so that when the event happens, we can see how the system responds to that.
That was very well said, Karim. So, yeah, the key here is that the system dynamics models are not simply projecting behavior off of past behavior. They're projecting behavior based on structure, and the past behavior is used to understand whether or not that structure is representative of what's happened. So looking forward, you're saying, well, if the same structure is in place, then how does that change? And it's stronger than that because it gives you the ability to say, well, if the structure changes, and we know how it's going to change, then what kind of behavior will result? And in that case, there's absolutely nothing in the past behavior that can inform that. You absolutely have to look at the structure to see what would be happening in the future anyway.
Okay, thanks. Bob, here's a question for you since you're on, which is perfect timing. Bob noted that Dynamo was a universal language. Who owns Dynamo? Was it sold? Is it free of charge? Where is it at currently?
Dynamo is no longer in use. The format for Dynamo did end up being showing up in a variety of different products, including the original Dynamo, which is a Hugh Roberts product, which is a small consulting and software firm out of Cambridge. There was a version of it done at Dartmouth. There was a version done in the UK called BizMap. I actually don't remember the Dartmouth version's name. So there are a variety of versions of it, all of which could use the same underlying language to do the simulation. This was before there was a lot of patent work and whatnot, so there wasn't ever any restriction on the use of that. That was imposed by anybody in the field at the time. But what's happened since then is there's been a lot of richness brought into languages, different ways of representing equations, new functional forms, different restrictions on variable names and whatnot. So it's changed. There's been a lot of, and the graphical representation, Dynamo was purely a text language like a software source code would be. There was no graphical representation at all in the original Dynamo language.
Okay, thanks, Bob. Here's our next question. Are you aware of the recent work on the BPSIM or BPSIM standard, simulation data for BPMN?
I have to say no, unfortunately. I'm not aware of it.
Steve, are you familiar with it?
No, but I want to say that you know, for those who haven't seen system dynamics models in the past, they can look very similar to business process models. You know, what you're seeing on the screen might look like a Visio diagram, except that a Visio diagram, the relationships between the entities are more representational than explicit. That is, I can draw a Visio flowchart, a business process model, and I don't have to be specific about the things that are in each one of the boxes that moving through the arrows. I can make up a different story for every business process, every time I present a business process chart. But in the system dynamics world, the rabbits in the box, you know, the deaths pertain only to rabbits. The births only pertain to rabbits and to a specific number. And so it's a very explicit language. It's actually a challenge for people coming from the process modeling world to read a system dynamics chart, as I can attest to myself, because it takes a while before you get used to the idea that every line and arrow that you draw has a very, very specific meaning and isn't representational. So it's a different way of describing relationships between things and the equations that govern those relationships.
Okay, we've still got the questions coming in. Here's the next one. I have existing models for marketing pipelines. Can I adapt them to this new standard? I use ISEE system software.
Yeah, so IC systems in version 10 for both I think and Stella are saving XMILE files. So if you have the latest version and you're saving your models, then you have adapted to the new standard as it is in the draft. It's possible that it'll change, but it's likely it'll change in several ways. But any changes that occur will be in the next version of the software. So you don't have to worry about that.
Steve, anything to add?
Nope, that was good.
Okay, here's another really good question. With an eye to mobile devices, what practical examples can the speakers think of that would make systems thinking available to the general public?
Let me just jump in here and say that with mobile devices, what you're really looking at is applications, not model development per se. And one of the big advantages of something like XMILE is it will allow different people to write applications using an underlying model developed elsewhere in a variety of different platforms, including mobile devices. So it actually opens up the universe of applications that people might be developing for things when there's a standard language that underlies the simulations.
Yeah, I think that's one example, Bob. The other example in a big data sense is that if you think about people using their mobile devices as a stock from a social media perspective, and you can design some really interesting simulation models using XMILE in which the people themselves are providing the live data, in which you can test, for example, a marketing model against, you can design a system dynamics model to test out different marketing scenarios. And capture live data from people's handsets as they tweet about different things. And so in some sense, that ability to link stocks and flows to live data now takes on a really interesting dimension when you link that to big data technologies that measure social media, and that you can think about every mobile handset as a part of your data set and run simulations against those.
Any more to add here? Okay, here's our next question. Can you tell us more about how patterns and trends in data inform policy assumptions?
Again, I would just repeat the structure versus data behavior, structures versus behavior dichotomy that's pretty well established in the field of system dynamics, that the model itself is a representation of structure. Patterns of behavior are manifestations of what that structure does when it interacts, as it interacts over time. And we're not projecting behavior from behavior, we're projecting behavior using structure and using that behavior to validate the structure.
And so in the sense, thank you, Bob, that was great. In the sense that we're looking at policies, we then apply those policies to that structure. So we have the structure, and it replicates the behavior from the past, for example, based on the data that we have. But we have that structure, and then we're going to apply this new policy to that structure and see what happens. It's completely different than trying to predict what's going to happen from data.
Okay. Here's another question. When I taught system dynamics 5 years ago, we were taught to keep it simple. It seems that this goes in other directions. Are we really ready to link simulations? Do we know how?
I don't think there's anything inherent here that makes it more complicated than the current set of models that are there. And as far as linking pieces together, I think we have a lot of work to do still there in the research area before that becomes a reality. But there has been work done on that. There is work being done on that. And I think it's possible. I don't think that the presumption of big data or the addition of big data makes this automatically become large, big, complicated models that we don't know how to connect together. I think, as in this example I just did here, there are very small pieces that can come together to help inform what you're trying to figure out for your it depends on your given problem. But again, you don't have to create a giant model just because you have a lot of data. We're aggregating the data, we're bringing it down, we're looking at it in a more homogeneous way, so the models can still stay relatively understandable. I'm not going to say they'll be completely understandable, but they can stay relatively understandable, and we can just do more research. I mean, there's a lot we can do to try to figure out how to link these better, and how to recognize that this piece can work with this piece, can work with this piece, can work with this piece. I think there's a lot of work that can still be done there and needs to be done, and I look forward to seeing it happen.
Okay, we've got time for a few more. And folks, if we do not get to your questions, I have recorded them, and we will get back to you with answers to your questions. So again, if we don't have time, we will address those in a follow-up email. Okay, here's our next question. Do you plan to extend XMILE to include discrete events, agent-based, or Monte Carlo simulations? And if so, when?
No. At the present time, I think that, as I said before, it's not really necessary for us to build one simulation language for everything. And it's out of scope for this initiative. I think it's enough of an accomplishment to socialize the ideas inherent in XMILE and system dynamics with a broader audience, to get feedback and input from people who probably have some fantastic ideas for coming to the process new. That already is a large international undertaking. So for version 1 of XMILE, other modeling disciplines and languages, while we're happy to be influenced by those who care passionately about them and have ideas, I think inclusion of those ideas in the spec is probably out of scope.
Any other feedback?
I agree with what Steve has said. I mean, this is an area that's dear to my heart, and I would very much like to see version 2.0 of the spec try to address some of these things, but it's definitely true that you need to get something done, and I think the current view that we try and capture what is done in a pretty classic system dynamics framework is the appropriate way to go.
Okay, great. You know, we've got quite a few additional questions here, and like I stated earlier, we will follow up in an email. I think we've got time for 2 more, so let me go ahead and give you guys this one. Can we apply such system dynamics models for simulation of value chain upgrading strategies? I think you touched on that earlier, but let's take a pass at that again.
The question is not, to my mind, completely specific, but the answer is definitively yes. You can look at the value chain of any organization or wherever the value is being added and see how that's happening. And the system dynamics model is definitely a good way to inform that. But without knowing more specifically which particular value chains they were looking at, I couldn't say much more than that.
Okay, great, guys. Again, we do have some additional questions. We are approaching the top of the hour. I would like to thank everybody for joining us today on our webinar, and we will follow up. We have recorded this webinar, and the recording will be available. Again, thank you, speakers. I appreciate your time, Steve, Karim, and Bob. Thank you. Have a nice afternoon.
Thanks, everyone.